Yeah. So, okay, I will start. So first, thanks everyone for coming for the Martlets Talk Season 4, Episode 4 by Dr. David Barton from Harvard University. And before I start, I would like to thank everyone who contributes to the talk, and especially Jingtian, who did a lot of work, coordination, and also planning for the events. So today's talk, first I will give a little bit of introduction on the society as well as some of other events in the society. And then Jingtian will introduce Dr. Barton, and then Dr. Barton will give everyone his talk. So then after the talk, we will have around 30 minutes Q&A sections, and everyone, you are free to raise your hand and ask Dr. Barton, and then we have a discussion on the topics. So let me introduce a little bit other events in our society. So the Martlets Society, which is like a platform for interdisciplinary exchanges for like young scholars. And currently we have mostly three kinds of event talks. Martlets Talks, which is for academic research exchange, and a WDA talk, which usually focus on the stories beyond academia world, and the TMS workshop, which is on building skill sets for PhD students and postdocs. We also have special issue based on the demands of our audience that we usually invite some senior members of academia, senior researchers to give some talks on certain topics, for example, research directions or on how to publish papers and to go for technology translation. So if you are interested in more of our events and more of our activities, you can visit our website and also send us emails if you want to become a speaker or a host. And feel free to follow us on our WeChat channel and also Twitter accounts. And then I will give the floor to Dr. Hu, who will introduce Dr. Barton.
So thank you, Zhen, for the opening remarks, and good morning, everyone. It is my great pleasure to introduce Dr. David Barton from Harvard University. And Dr. Barton is currently the Intelligence Community Postdoc Research Fellow in the School of Engineering and Applied Sciences of Harvard. And he had his bachelor's degrees in chemical engineering from University of Minnesota in 2015 with the highest honor. Sorry, I couldn't pronounce the Latin words. He went to the Stanford University working with Professor Jennifer Dion, who is a rising star in the nanophotonics field. After graduating in 2020, he started his current postdoc appointment at Harvard University with Marco Nonkar, working on nonlinear and quantum photonics. So before, I don't know David in person, but my former colleagues from the Odom group at Northwestern University had a chance to attend one of his talks and was very impressed by his research. So that's why we decided to invite him here. So today he will share with us his work on reconfigurable flat photonics. And I have also worked on this field for years, so I understand exactly how challenging it is, and also how exciting and important it is. So David, all yours.
Yeah, thank you so much for that introduction. Yeah, so I'm about a year and a half into my postdoc here at Harvard, but the presentation I'll be sharing with you today is kind of a mix of the things that I've done in my PhD and postdoc, and there's kind of a connecting thread between them, both in using resonant and electro-optic materials to design structures that we can dynamically sort of shape light either in space or in time. So let me first get a laser pointer here. Yeah, so since this is a bit of a general audience, I thought I would start out, somewhat broad to maybe describe why I think some of this work is important and useful, and to give a very broad context. I think we're first going to go back in time. So this is actually a paper that was examining the role of evolution of tetrapod animals that were starting to grow legs and move out of the ocean and move onto land. And so you see going top to bottom is sort of the evolutionary time for these creatures. And so, the first thing that these animals did was to rise to the top of the ocean and actually look of the water. And what happened is they found that the optical density of air is actually about 100 times lower than the optical density in water, which means that they can see about 100 times farther. And so in response, their eyes move to the top of their head. They're sort of exploring, the environment above them. And then upon realizing that you can actually see, maybe a football field worth of distance, these animals actually ended up evolving to have their eyes triple in size. And so what that meant is now they could actually see and receive a lot more information from the sunlight. And when they finally, evolved legs and started to move on to land, it's actually sort of hypothesized by evolutionary biologists that there was an evolutionary need to process all of the complex information in their new environment. And there was an evolutionary advantage in developing new processing in their brains that allowed them to deal with all of the new information that's coming in. And so the reason that animals that and creatures that have had any evolutionary history above land tend to have more advanced information processing capabilities comes from the need to process optical information. And so, maybe put into more of an engineering sort of context, if we look at, the typical data speeds that we have on, broadband or high-speed internet that we've, been engineering for years, we're getting maybe around 100 megabits per second is a fairly standard number to get. But, estimates for the amount of information that the eye will actually receive in any given moment is actually much higher. It's actually around gigabits per second. And so it makes a lot of sense that there requires a lot of resources and a lot of development of, the human brain or the animal brain to be able to distill the necessary information and process it quickly enough to be able to respond to new and emerging cues in your environment. And so, as engineers, we've also been using light for a long time to be able to process and send information. So this is a plot or a map of all of the submarine fiber that's used for high-speed, long-haul data information that's being sent all across the world that allows us to have these sort of Zoom calls and these sort of seminars. It really comes down to the ability to engineer and shape light in particular ways to send useful information at very high bandwidths and at very high rates. And so, as we sort of think about these new and emerging technologies that we've been seeing actually a lot of interesting headlines recently, there's a lot of spaces where our ability to engineer light and its interaction with matter will have really profound impacts on the way that we sort of interact with the environment around us and actually are allowed to, sort of make changes to our decision making. And so a couple of these examples are in artificial or virtual reality, where you want to project or see different information and interact with that with our actual natural environment in new and interesting ways. Or another typical example is optical ranging or LiDAR applications, where you want to be able to sense your environment and make quick decisions to make, for example, driving much safer. And so there's a lot of space here to be able to engineer light in new and interesting ways for these sorts of technologies. And actually, developments in nanofabrication have allowed us to do a lot of really amazing things in this space. And so very analogously to the transition from vacuum tubes to integrated circuits, being able to actually put things onto a chip and make them very small and densely integrate all of these things allows us to do a lot of things that we would never have previously imagined. Being able to have a mobile device on your phone that allows you to search information compared to what we had maybe 70 years ago, where we had these large banks of vacuum tubes to try and do our computation. And so we can actually use these sorts of technologies in a variety of different contexts. And so, a classic example may be designing new materials or new structures that allow us to dynamically change some optical operation. So one example is maybe taking something from a DSLR camera where you have these large lenses that have very particular distances between each component that will then focus a very nice image onto your camera. And so finding ways in which we might be able to shrink all of that down and find applications, for example, maybe on a contact lens, that allow us to shape light in interesting ways, change the focal length without actually moving any sort of lenses, or to project information within the field of view. I think all of these are very exciting areas to work towards. In this sort of picture that I showed earlier with putting a bunch of components onto a chip for electronics have sort of revolutionized the electronics industry, but the same thing is actually also happening in photonics. Being able to put all of this onto a chip, use similar nanofabrication technologies, allows us to design new elements that we can densely place onto a chip and scale down a lot of components that you might have seen or you might have maybe on an optical benchtop. And so there's, being able to actually deploy some of these new technologies in spaces where they never would have actually been able to fit before. This is a photo of IBM and working in sort of silicon photonics. But what I'll be sharing with you today, the first half is going to be on designing reconfigurable flat optics and demonstrating some new interesting design modalities, which is the main focus of what my PhD sort of was. And then the second half of my talk will be in the space of integrated photonics and shrinking down optical components and designing new devices on a chip. And I think in the abstract, I had also mentioned a couple of different projects. Having sort of put together the slides and realizing, I wanted to be maybe a little bit more didactic in my explanation. We may not actually get to the last portion of this talk here. It really depends on sort of how long it takes me to get through the rest of the material. But I am happy to talk about some of the devices that we've made sort of in that space. So first, we can get started with these sort of reconfigurable flat optics. And so if we go back to this picture that we had, this DSLR camera, we have these very well defined optical components like lenses, where you have a piece of glass that has a very well defined shape that's ground into the surface. You polish that in extremely well to make this high quality sort of optical component. And these are, relatively thick if you've ever worn glasses or if you've ever done anything on an optical table. I mean, they take up a fair amount of space. What we can actually do is shrink it down to fit on top of a chip using nanophotonics and create what is called a flat lens. And so at least on the x-axis, this is a top-down optical image. This length scale in this direction is pretty comparable. But if we actually zoom in and take an SEM image, what these are actually composed of are a large number of these dielectric antennas of different materials, silicon dioxide. There's a variety of different materials you can use. But by changing the shape and structure of these, you can interact with light in very particular ways. You can define the response that this light will see and change the amplitude, the phase, the polarization of light in any way that you might be interested in. And if you spatially array these, then you can perform operations that you have in virtually any other way that you have in bulk optics. So in this case, you can design a structure that is flat, that's maybe only a few microns tall, that will be able to focus light to a point in the same way that a lens does. And so you can scale these things down to really very thin formats that all sort of fit on a chip. This field of flat optics or metasurfaces, there's a wide variety of places you can go with this, from lensing to designing new lasing sort of devices, nonlinear optics and doing some beam steering, even more advanced technologies like making holograms, where you can project a particular image somewhere in space, or even more exotic in terms of cloaking, where you can actually hide objects from view. All these can be done because we have this very sort of exquisite control of the optical response of these materials by their sort of nanostructuring and their design. One challenge in these sort of structures is that they're really dictated their response is dictated by their geometry. And so by way of example, we can make structures that will, we can design these sort of optical nano antennas. So in this image here, I have a block of silicon that's 300 nanometers tall that is just going sort of in and out of the page just for, like a simple example. And if we send light through from the bottom and record the transmission coming out the top, there's some interesting things that are happening. So we see that there are actually two different regions where the transmission actually goes to zero. Everything is sort of reflected or absorbed. And if we sort of zoom in and actually simulate what this response actually looks like, now this sort of rectangle structure is the silicon that we were talking about sitting on a substrate. And then the plots here are either the electric or the magnetic field of the light locally in the material. And then these arrows are actually showing the relative field orientation. What we find is actually the red and blue regions that correspond to these dips are actually these optical resonances that actually mimic the look of various dipole sources. So if you think of a canonical standard sort of electric dipole where you have the electric field sort of circulating around, or in this case, a magnetic dipole here at the bottom, where you have an electric field circulating around in this sort of orientation, we're actually able to shape the local structure that this light sort of takes on. And so this is interesting. We can design a lot of things with these sort of optical resonances. That, one challenge here is that the transmitted intensity goes to zero, so you don't really have a whole lot of light going through, which is maybe not that useful. But if you then engineer the material differently, and you, for example, make your structure very tall in this image on the left, the position of these resonances actually shift and they align on top of each other. What we end up finding is that the transmission actually goes very, very, very high. So you can get nearly 100% transmission when these resonances sort of overlap. And so if you, if you've ever worked in the field, this is called a Huygens type metasurface, and it's just sort of well known that you can get these resonances to overlap, and then your transmission will go up. And so this is one common way of designing these sort of metasurface elements. We can actually go, one step further. If we have these tall nanostructures, now I'm showing a simulation of light propagating through the bottom, up through these silicon antennas, and then coming back out the top. If we then change the width of these bars, we actually engineer what happens to the scattered phase. And so in this example, if I have 210 nanometer wide nanobars, and then I put it next to bars of different widths, you can see that the light that is exiting has a difference in the total phase. This red part, the peak of the electric field, is slightly different than the previous or the neighboring element. And so if I continue to put these in line with each other, what we actually find is that while we have a well-defined wave coming in that's propagating directly up, the individual phases of these elements actually build up and allow light to be redirected to a well-defined angle. So in this case, light is now being directed up and to the left simply by changing the structure of the underlying material. And so if anyone has worked in this space, what we're doing is we're changing the width of these bars, and we're looking at the amplitude and the phase response of the scattered light. And we're choosing elements that have well-defined phase differences that we can use to build our structure. And of course, you can go much farther than this. You can build structures that lens, you can build all these holograms, et cetera, come from this sort of design principle. But the key challenge here is that the phase delay is set by the geometry. It's set by the optical properties that are defined in space. And so one thing we wanted to do is find ways to make this tunable. And the way that we ended up focusing on this, looking at these sort of applications, one is to design structures that you can, for example, dynamically steer what direction light is going. And in this way, you might be able to use this in a LiDAR application where you want to scan in space where and look at the reflected signal and be able to build out where objects are in space. Or in the example previously with the DSLR, if we want to be able to stretch or change the focal position, we would be able to have maybe a solid state camera where all we have to do is change voltage and get a different focus. But the amplitude and phase of these structures are actually set by the geometry and the refractive index of the materials. And so you have to do one of two things. You either have to change the geometry or you have to change the refractive index of these materials. And so since the geometry is typically set by nanofabrication, one common way of doing this is by changing the refractive index. And there's a variety of ways you can do that. One is with liquid crystals. You change the orientation of the liquid crystal. Another option is to physically actually move the entire structure up and down using, for example, MEMS. And then there's some other fancier maybe ways of doing this where you're changing the properties using maybe E and Z materials. And I'm happy to talk about that in later on. And so these are sort of emerging ways of doing things. They all have their advantages and maybe disadvantages. What we ended up pursuing is ways that we can enhance the light matter interaction within the material itself by its sort of very structure. And for that, we ended up looking at the sort of nonlinear optical properties of materials. And so these are potentially, I think I have one more slide where I show some sort of basic equations. But here, very briefly, the refractive index of material is given by the square root of its permittivity, certainly at optical frequencies. And this permittivity value is dependent on a variety of different components. So one is the linear relative permittivity, something on order of 1 to 10. All materials will also have this nonlinear component here, this chi3, that's dependent on the intensity of the electric field that's within the material. So if I increase the intensity of the light, what this tells me is that the optical properties will change, but although very weakly, because this parameter is about 20 orders of magnitude lower than its linear response. And finally, the last component that I'll be talking about today, some special materials and ones that I'll talk about today have this second order nonlinear response, which is only linearly dependent on the electric field. And this only exists for materials that lack centrosymmetry. So materials like silicon don't have this in bulk, but materials like lithium niobate that I'll talk about in a little bit certainly have this. And so if we want to enhance any of these effects, we can do a couple of things. One, we can have very long devices, have bulk crystal. We can use very high laser powers, or we can design structures that allow us to amplify locally what the electric field is. And so this is the approach that we ended up taking. And we ended up designing high Q resonances. So this will come up a few times in this presentation, so I just want to sort of walk through this. This is actually a structure of an optical waveguide on a chip connected to this large ring. This ring is a cavity that will trap the light inside it for a long period of time. And so light will propagate along this direction in the chip, and then it will end up coupling into this ring and circulating for a long period of time. And you can compute or measure the lifetime within the structure, and we can, researchers can find in this case that the light is actually trapped in this 100 micron structure for several nanoseconds, which is actually extremely, extremely high. And if you were to take the Fourier transform of this transmission, what you would find is that you have these very narrowband resonances that appear in the transmission spectrum that are defined by a quantity that I'll talk about called Q, or the quality factor, which is defined as the sort of the wavelength of the resonance divided by its line width. And so in this case, we're able to get quality factors that are on the order of maybe 5 million, which means that light is trapped inside the structure for an extremely long amount of time. If you back out the total size of this cavity, what this means is that light will circulate in this cavity tens of thousands of times before actually exiting. And so what that means is that the local light intensity will actually go up quite a bit because light is stuck in there for much longer. And so this light intensity is then proportional to this quality factor. And so we can use this lifetime buildup to actually enhance the light matter interaction and allow us to do a lot of very interesting things. And so actually, to maybe put all of this in a plot, on the x-axis, we're nominally looking at this quality factor parameter that I just talked about. And then on the y-axis is this maybe semi-quantitative plot that talks about the ability to sort of shape light in space. And so these are the typical elements that are used in metasurface elements, these bars or these nano antennas. but their ability to actually control light sort of in time is maybe a little bit more limited than what you have in photonic crystal nanocavities, these larger ring resonators. And so if we can fill in and design elements that fit into this red box, what this allows us to do is very efficiently engineer the wavefront and also get access to these nonlinear optics components, which allow us to dynamically and make reconfigurable these optical components. And so this red box was basically the focus of my PhD. And the big challenge is that these structures that I was showing earlier are actually quite large, on the order of microns, tens of microns, or even larger. And so what that means is that you can't actually design these nano antennas that have to be very, very small. And in fact, when you scale these down, like I showed you in the plot earlier, typical nano antennas are quite small, but their quality factors are necessarily very low by their sort of design. And so finding ways that we can engineer and combine functionality from these sort of micro resonators to these nano antennas would be quite powerful. And so we actually do that is actually using the same sort of design that I showed earlier. We have these arrays of these bars. And if we do a full sort of simulation, we have light coming in from the bottom, we can redirect it to a particular sort of direction, in this case, about 45 degrees. And so this is maybe a standard way of designing things, but we also know that this structure is a bar of material that has a higher refractive index than its surroundings. And so what this means is that it actually has a whole spectrum of guided modes that actually will propagate in and out along this bar that can be sort of trapped in the same way that maybe an optical fiber does. And it can guide light in very particular ways. And so if we actually sort of look at this, if we're looking at maybe 1500 nanometers, and I look at a cross section of this sort of structure, and I'm looking here at what the mode looks like that's guided in and out of the page. And so we see that actually there are a whole series of guided modes that will appear in individual bars because the refractive index, in this case of silicon, is actually high enough to allow this sort of guiding to happen. And so actually, what we came up with was the ability to interact with these sort of guided modes. And so if we include into these nanobars these little grooves that appear periodically, this wavelength or this periodicity of this structuring corresponds to the guided mode wavelength of a mode within this nanobar. And so when we send light in from the bottom, what we actually find is there's a narrow resonance that opens up in our diffraction spectrum or beam steering spectrum that corresponds to this guided mode that we find in these nanobars. And if we look at that particular wavelength, we can actually simulate what this looks like. And what we've done is we've formed a guided mode resonance in these metasurface elements. And this local field buildup actually on this resonance, the field intensity is actually dramatically enhanced compared to free space. So the local electric field is actually over 100 times higher than it would be for light just traveling through it without this sort of resonance. And so we actually went about and made a whole large of the number of these sort of samples. This is just a top-down SEM of what a typical sort of structure looks like, and maybe a zoomed in structure here. We have a beam steering element that we've designed where we put in these sorts of grooves. And so if we do these sorts of experiments, what we actually find is that we can design these high Q elements in beam steering metasurfaces and in really any sort of nanophotonic sort of structure. And so we designed these to have to beam steer into this plus first order. So light is being diffracted to about 45-degree angle. And we actually have this high Q mode that actually appears in its spectrum. And if we were to actually extract the quality factor of this by looking at its line width, what we find is that we're actually able to engineer a quality factor in this case of about 1500 in this structure. And so, this is very interesting. This is maybe a 2 order of magnitude improvement in the quality factor of these sorts of devices. And it's also the first time we've been able to demonstrate this in these sorts of, in this type of nanophotonic structure. But we can play a lot of games with this. So we also made a series of samples where we changed the geometric parameter of this structure. So these are all SEM images. And then we have the diffraction into the first order and the extracted quality factor. if we change, for example, how strong this perturbation is, we can actually change, roughly speaking, what the quality factor is. And so as we make them smaller and smaller, the Q factor actually gets quite high, in this case about 2500, which is just dramatically higher than what you would typically have in these sorts of elements. And so this is really great. The highest Q we were able to get is about 2500. And we can also, go further, and we can dynamically or deterministically decide where these resonances actually occur. And so if we change the period of the structure, we can actually place exactly in frequency space where we want this to occur. And so here, by changing the period by about 20 nanometers, we can actually change where the resonance appears by shifting it around. And so what this really showed for the first time is that you can design these individual nano antennas in these sort of metasurfaces to design ultra sort of high quality factor sort of devices. And this is built in silicon, which, as I mentioned, is centrosymmetric. So it does not have that chi2 parameter, but it does have this chi3. And so we played a couple of games with how we might be able to, do interesting things with this. So the first thing that we did with this sort of structure is to say, well, what happens if we crank up the power? So in this structure, we were able to design nanostructures where we have a reasonably high quality factor, again, in this sort of beam steering response. And locally, the field intensity is amplified quite a bit. In this case, the maximum is about 160. But on average, the electric field is actually enhanced by about a factor of 100. And so using this sort of chi3 parameter, what this means is that we're able to amplify this Kerr effect by about a factor of 10,000. And so what that means is that if we crank up the power, we can change the permittivity and start playing around with the actual response of this device. And so to sort of demonstrate that at low power, if we look at the diffraction efficiency, if we increase the power, this resonance will actually shift over because the refractive index is being changed. And in doing so, if we actually look at a particular wavelength and see what happens as a function of power, we can dynamically change what the diffraction actually looks like and what the sort of wavefront shaping is doing simply by using power as sort of the tuning knob. And so in this case, we can turn on and off the ability to redirect light to a particular wavelength. But we can also do even more than that. We can design lenses. So here, we again put in this guided mode into these nano antennas. And we are able to design a structure that focuses light to a point. So this is the focal point of this lens. And if we turn up the power, we can actually reduce the ability for it to focus. So we can actually, and we can also change what the focal length actually is. So using power as this sort of tuning knob, we have the ability to dynamically change the response of this sort of focusing element. And so, that's all great. That's all, maybe useful in certainly in applications where you have high laser powers. But, we were looking for ways that we could do things without having to change the power and maybe have something, solid state. Can we interact with light in interesting ways using applied electric field? And for this, the material that we ended up settling on is lithium niobate. So this is a schematic of the crystal structure of lithium niobate. In here you have, in red, we have these oxygen atoms that form a hexagonal crystal structure. And inside the octahedral interstitial sites of this lattice, we have alternating layers of lithium and niobium. So niobium is this very large blue, and lithium is this smaller yellow. And actually, what is maybe quite important about this is that the relative position of the niobium and lithium atoms is not exactly within the center of that interstitial site. And so what this means is that this material is electro-optic, and it's also a ferroelectric material because it is not actually centrosymmetric. And actually, it's quite a very, very useful material because it has a relatively high refractive index, so we can do a lot of engineering with it. It also has a very large chi2 nonlinearity, and for its electro-optic response, this parameter is actually very, very high for materials that we can grow and use efficiently in sort of deployable products. And so what this means is we can apply an electric field and change the optical properties quite a bit more strongly than you'd be able to with materials, for example, like silicon. It's also a high bandgap semiconductor, which means that it's actually transparent over a very large window. Its bandgap, you'll start to see absorption on onset around 400 nanometers, depending on how it's made, and it's transparent down to about 5.5 microns. So it covers most of the visible and certainly telecom, and also into sort of the mid-infrared. And there's other interesting optical properties. I mean, it's space group, it has a lower degree of symmetry. So the material is also birefringent. So there's a lot of interesting games that you can play here. So, I mean, what we did is to use the fact that lithium niobate can change its optical properties using this applied electric field. And we designed structures that give us dynamic and tunable sort of responses. So here, we designed a structure that acts as a beam splitter. So light will come in from the bottom and will be redirected to propagate in both the plus 45 and minus 45 degrees, effectively splitting the light in two. And so this is quite useful in a variety of different optical components, especially in tabletop sort of setups, or there's plenty of quantum measurements that you have to do that require beam splitters. And we were also able to engineer in a high Q resonance into this structure. And so we can get very efficient beam splitting and also design these high Q resonances. And so if we design a structure here where we have a couple of unit cells of this device, we put contacts on the left and the right, we can actually show that we can change the optical response of this material. So for example, by applying no voltage whatsoever at this wavelength, around 1400 nanometers, we get direct transmission, but by applying a voltage, we can split the light into two propagating directions. And so we can go from having just a solid sort of beam splitter, meaning now we can have a dynamically tunable or modulatable sort of optical element that requires just a driving electric field that we can do simply by sort of wire bonding our structure, putting it in, and then just changing the voltage. And we actually also went a step further. After I graduated, a couple of students in my old group moved on to design structures where we take an individual nano antenna and we apply a voltage going through the material. Here in gray is silicon, and then underneath is lithium niobate. And what this allows us to do is individually control the response of each of these nanostructures. And by applying voltage, we have nearly 2 pi phase control, which allows us basically to completely control the phase response of this material. And with this, we were actually able to show a variety of ways where we can dynamically change the beam steering response and make a high efficiency, very fast and dynamic beam steering element simply by changing electric fields and voltages that can be very easily sort of controlled. And so what this allows us to do is have this very sub-wavelength, very small, compact device where we can dynamically change the optical response driven entirely by an electric field. And so we think this is a very powerful platform to designing these sort of optical elements and making them completely sort of reconfigurable. There's also been some other things done at Harvard. I just thought I'd toss these out. Of course, there's a lot of work that's being done in making these high Q materials, making, for example, spatial light modulators, things like this, using, for example, electro-optic materials, in this case, using a polymer. I think this is actually, since I made this slide, has actually been, I think, published. And actually, moving even beyond sort of these sort of augmented or virtual reality sort of applications, LiDAR, things like this, we were also able to show that by slightly changing the design, we can actually have very, very, very dense biosensors. And so this was actually done by a graduate student in my old lab after I left. But by functionalizing the surface of this material with something that can bind selectively to particular biomolecules, we were also actually able to show, in the sort of disease of the day, that we can have a very specific and fast sensing platform for sensing, for example, SARS-CoV-2. And so you can do different surface functionalizations to this, and now you have a very dense array of effectively pixels where you can do different sensing modalities. And in this case, we're able to sense gene fragments from the coronavirus So we think this is very powerful sort of for technologies that span a lot or basically any optical sciences. And so in the future, there's a lot of interesting things that could be going on here. And so maybe to wrap things up of this portion of the talk, what we were able to show is that using guided mode resonances, we can actually tap into this square and actually get this sort of dynamic wavefront engineering and access to this sort of reconfigurable photonics. And so to fill in this chart with my PhD, that's basically what this is. I actually put a timer in here, and it turns out that I did wax quite eloquent on my PhD. So I will briefly go through some things in my postdoc for lithium niobate sort of integrated photonic devices. But maybe to sum up the metasurface work, what this really shows is that there's a deterministic way of engineering the light matter interaction between individual nano antennas and interfacing them either with strong optical fields or with electro-optic materials. We can get dynamic modulation and make reconfigurable dynamic devices on a chip. And so we think this is a very powerful platform sort of moving forward. And so, yeah, like I said, we'll sort of briefly talk about the integrated photonics work that I've been doing. This is using lithium niobate on insulator. And this bottom section, I won't really be able to quite talk about, but we'll be talking about ways that we can design new and interesting devices that control light in a variety of different ways using the electro-optic effect in lithium niobate. And actually, I maybe talked about the beginning of this work by talking about long-haul, telecom, being able to connect the world around us and be able to have Zoom calls like this happen with very high speed. And that's actually really thanks to lithium niobate in particular. And it's actually being used in both telecom and datacom and high-performance computing. And it actually is because it is one of the best electro-optic materials that we can grow in very large volumes. That allows us to make actual bulk modulators. So on the bottom left is actually a snapshot or a picture of one of these devices where we have optical fibers coming in, we have a bulk crystal, and we have light coming out. And what we're able to do is actually make these optical waveguides inside of lithium niobate by diffusing titanium into the structure. And by applying an electric field in one section, we can actually convert electrical ones and zeros effectively into optical ones and zeros by changing the actual output response. And this is done entirely because of this electro-optic Chi2 parameter that only exists in non-centrosymmetric materials. And so that's typically done like this, where you dope titanium into particular areas of your lithium niobate, and then you put down contacts that you apply an electric field to. But the challenge here is that the index contrast when you add in titanium is actually not that large. And so you need to have effectively just very large waveguides that are comparable to maybe optical fibers. And because of this, the devices are quite large and your electrodes need to be spaced quite far away to get the response that you need. And so that kind of requires you to have devices that are relatively actually quite large. But recently people have been able to commercially deploy thin film lithium niobate. So that looks like the bottom left here, where we have a silicon wafer, silicon dioxide handle or a baried oxide, and we can actually deposit or bond thin film lithium niobate. And developments by both my group that I'm currently in, as well as many other groups around the world, have been able to engineer new ways of nanofabricating this material and making very high quality optical waveguides on a chip that allow us to make very efficient, very high speed and low energy, so sort of modulating devices that can actually compete with or outcompete devices that are commercially deployed in their bulk sort of counterpart. So this sort of scaling down not only makes these devices smaller, but it also makes them better. And so actually to show that, this is a photo from before I joined the group. On the right-hand side here, you have a conventional electro-optic modulator. And then in the center here that has this red laser going through it is actually the chip that has one of these modulators on there that allows us to do things at very, very, very fast rates. And instead of a standard scale bar, we have a quarter here, just showing how much smaller we can make these devices. And so what I'll be sharing with you today is our work in designing structures, that can do very interesting things to light in time. So whereas my PhD maybe shaped light in space, my postdoc has been focusing on ways that we can shape light maybe in time. And one thing that we're interested in is designing sources of pulsed light. And this is actually very common throughout all of photonics and science in general, spanning sensing like LiDAR and chemical imaging technologies to quantum photon sources and resources for quantum computing, as well as precision sort of metrology, for example, in stabilizing atomic clocks. And so this is useful in spectroscopy, in quantum optics, metrology, sensing, biophotonics, all over the place, really sort of rely on these pulsed laser systems. And if you've ever seen one in the optics lab, this is maybe a photo of a titanium sapphire laser right here on the bench top. And so you can actually generate and design these very nice lasers, but they take up quite a bit of space on a bench top. And so one thing we were trying to figure out is whether or not we can actually put these onto a chip. And so to sort of briefly go through this, any sort of pulsed source is actually going to be a frequency cone. And so if we look in the time domain, we have these pulses that will arrive in time that have some given envelope. And if you actually take the Fourier transform of this, or if you look at its spectral components, what you actually find is that these pulses are composed of discrete lines in frequency that are spaced by a well-defined parameter called delta F. And this actually corresponds to the difference in the arrival time between the two different pulses. And then there's one other component, this FCEO, this envelope offset frequency, that defines the phase slip between the pulse here and the pulse here. The field looks slightly different at the sort of peak of the pulse envelope. But with these two parameters, you can actually define the entire spectrum of a frequency cone. But I mean, it is a pulsed source. You have sort of broadband sort of light coming with it. So the smaller the pulse, the larger the frequency spread that you have, or the more colors that you have in your pulse. And there's actually a variety of different ways of trying to do this on a chip. A couple of things that I'll be talking about. One is using this Kerr effect that I mentioned earlier, and another one is using these sort of mode-locked semiconductor lasers on a chip. And again, these have their advantages and disadvantages. But we're going to talk about ways that we can do it with electro-optics, where we can send in basically a microwave tone, and we actually end up getting pulses that will come out that we can tune their operating wavelength, their repetition rate, and also potentially make these very high power. And so the way we're actually going to do that is using this concept known as Akhmanov's spacetime analogy. And so this is the last set of equations that I'll show you. And the only thing I want to get across here is that the equations that describe how light will diffract in space and the equation that will describe how light will actually, a pulse of light will will disperse in time, are actually have the same exact sort of functional form. And what that means, what this space-time analogy means, is that we can take parallels and we can draw parallels and analogies from the way that we engineer light in space, and we can apply to how we can engineer light in time. And so if we take a basic component like a lens, here you have a couple of different components that focus light to a point. Your lens has a particular size, so it basically has an aperture that will focus only a certain part to a point. Then your lens has a particular shape that will give a phase profile to this light. And then you have to let it diffract over a certain distance that allows all these components to focus. And what you get at the end of the day is a focal plane where you have the focus is actually defined, and the maximum focus you can get is limited by the diffraction limit. Here, you can actually map each of these components to doing this in time. And so you can actually send in continuous wave light of a single frequency. And at the end of the day, you actually end up getting pulses that come out. And so to show that maybe a little bit more explicitly, if we send in light that has one frequency component, one very nice laser coming out of a laser diode, if we send that through an amplitude modulator that changes the allowed amplitude with time, we actually end up carving out the same aperture function that a lens might have. Then by sending it through a phase modulator that we can give it a parabolic phase, it maps almost directly to the sort of phase profile that a lens will actually give you. And then in this case, if we let it go through dispersive material, where the refractive index changes with frequency, this will actually act as the focal distance that a lens will normally have. And what you end up getting at the end of the day is a pulse in time that can be limited by the bandwidth product. And you have different frequency components that will all line up, that will sort of spread out those frequency components. So anyway, so this is basically the gist of how this device sort of works. This has been done in tabletop by using a couple of lithium niobate amplitude modulators, phase modulators, a variety of microwave equipment. Actually, a lot of controls go into these sorts of measurements. And what you end up getting, in this case, for this specific example, you end up getting about picosecond pulses. And if you look at their frequency components, you see that there's a variety of different frequency components that span about 10 nanometers here. And these are actually very flat frequency comb lines that you can, for example, use in communications. For example, you can modulate on individual frequency components and actually send information along each of these different comb lines. But anyway, so this is the chip that we ended up making. Our scale bar here is a penny, and this is the device that we made on thin film lithium niobate. And if you look top down, there are a variety of different components. We can very efficiently get light onto our chip with these mode couplers. We have an amplitude modulator that we designed. We have a variety of phase modulator. We have one amplitude modulator and we have one phase modulator. And then we had to do a lot of design to try and get that to sort of dispersion on a chip. But at the end of the day, what we're able to do is take our device, we put it into the lab, we put a DFB laser right next to it, or you could bond it onto the chip. And if you turn the light on and you turn your microwave source on, what you're able to do is split this pump light into, in this case, about 13 or 14 nanometers of bandwidth. And not only that, but we can actually turn this continuous wave source into a 500 femtosecond laser pulse that operates at 30 gigahertz of a repetition rate by putting it through, in this case, about 60 meters of fiber. But we have this very nice chip here that's maybe an inch long, but then we have 60 meters of fiber. And so one question that we had to address is ways that we engineer dispersion on chip. And how do we shrink down this 59 meters of fiber into something that can fit on a chip, basically. And so the first thing we tried doing was basically to design a very dispersive waveguide. And I'm happy to talk about this later, but this required making a sort of lithium niobate, and our fab process was able to basically design structures that are about 100 times more dispersive than fiber. So we could convert this 59 meters of fiber to 50 centimeters of integrated waveguide. The challenge is that our fabrication process is not quite good enough to do that and get a lot of light out. So we ended up only being able to do partial compression. So here, by only using 10 centimeters of fiber, we could convert this pulse to about 8 picoseconds. And so what we ended up doing was making these sort of chirped Bragg gratings. So this, we basically have alternating layers of thick and thin waveguide that will reflect light at different positions. By changing the period of this, we can actually change the wavelength that's reflected in space. So maybe blue light will be reflected earlier on, orange, and then red light would be reflected at different positions. And this allows us to have this spectrally dependent reflector that becomes a dispersive delay line. And so given the timing that I see here, I'll very briefly go through how we actually characterize this, but we made a series of devices and we're able to actually engineer the reflection spectrum right around where we have our pulse coming in, and we're able to engineer the dispersion by changing, we can characterize this by fitting the spectrum. And what we find is that for something that's 2.5 millimeters long, we can actually get this dispersion to actually work quite well. We also fit the loss for this. The propagation loss is extraordinarily low. It's about 0.3 dB per centimeter, which is some of the lowest that's ever been reported in lithium niobate. We were able to actually change the dispersion here simply by changing the length. So for the given pulse that we want to compress, we can select deterministically how long we want this waveguide to be, and then go ahead and add it to our chip. And so these are also very high reflectivity, so it's a very low loss sort of structure. And so we actually found the optimal design for this, and we're able to actually fully in this case, on 2 different chips, fully compress our laser pulse to 540 femtoseconds. And the size of this grating is actually about a factor of about 30,000 shorter than what you would have in your single mode fiber. And so what this means is that we can actually fit all of it on a chip So this is a picture of actually two devices that we ended up making. We have an amplitude modulator, our phase modulator, and then our dispersion control is actually right here. And we're able to actually get the pulse to be about its bandwidth limit, limited only in this case we had a little bit of sort of fab mishaps, so the signals may be a little bit lower than it should be, but in principle we can actually do any sort of pulse compression that we want on this chip and design these femtosecond pulse sources that now can fit, for example, on your phone or in a pocket. And so maybe as an overview here, what we're able to show is that we had flat top frequency combs that we can use with electro-optic time lenses. We can engineer the dispersion on a chip, and because of that, we can generate bandwidth limited optical pulses, in this case, femtosecond pulses that all fit on a chip. And so as I sort of expected, I've gone already over time, but what I've shown you maybe today in this presentation is the ability to control light in space and in time using strong light matter interactions and using electro-optic materials. So here, there's some funding sources from my PhD and from my postdoc, but we've been able to do things to generate both flat optical components that we can dynamically change their response, and we're able to control light on a chip for future communications computation platforms. And so with that, I can sort of take any questions.
So questions. I actually have a question first for the reconfigurable part. So because I also work on this field, there are several systems like this patterning the nano antennas on the flexible substrate and stretch it mechanically or using the electromechanical actuators. The disadvantage is obvious. It cannot do single unit actuation, right? You can only control the global change of the system. And there are also GST is a phase change material system that can allow the unit-wise tuning, but the efficiency and it is only a binary tuning anyway. So that also has great limitations. And in your system, I can see a combination of both. So I want to ask you about the region of the upper limit of the system. So is it generalizable to 0 to 2 pi phase change? That's the first one. And I think also it would be really nice if we can generalize it from 1D to 2-dimensional control.
Yep. Yeah. I mean, yeah. I think you very succinctly sort of summarize the entire field of these sort of reconfigurable photonics. We have designed structures, and actually there was a nanoletters paper that came out in 2022 in late February, I want to say. We were able to do, at least in reflection, design structures that have full 2 pi phase control. So this allows us to design anything, at least with a one-dimensional sort of operation, to have the complete sort of control. And one of the sort of benefits is that these materials are extremely low loss, and we have basically control. We can set whatever phase we want by changing the voltage. So I think those experiments are certainly ongoing in my sort of old group at the moment. But yeah, so moving this to 2 dimensions is certainly possible. The design is a little bit more complicated. And so I think that's actually sort of an open problem that we're currently working on to enable that. Because yeah, you're exactly right. We can steer beam in a particular plane, or we focus light in a particular plane to a point. The ultimate dream would be to have something that can operate in both of the dimensions that you have on a chip. And so I think it is definitely doable. Design, I think, is still sort of ongoing. Yeah. But yeah, you're right. Actually, like phase change materials is a really, really excellent platform. I think there was a Nature Nano paper that came out not too long ago where they were able to get somewhat continuous sort of tuning. At the end of the day, the challenge in all of these is, there's always going to be some limitation. For us at the moment, it is, the fact that it's one-dimensional. If you're using phase change materials, you need to be, you have to send in these voltage pulses to change the refractive index, and getting low loss phase change materials is sort of like an evolving field. So to get
the papers you're talking about are either the Mark Brunsma's one or the Zhen Hu's one from MIT, right? I think those two came out at the same time. Actually,
yes,
I think if you can do like do 0 to 2 pi in the 1D design, it's already as good as we need, right? That's already the ideal system. But I think what they had in the Nature Nano paper is it seems to me is a less competitive system for and also achieve only 1D. Do you have any clue why that one can get you in your get you into that journal?
So I thought a lot of the results that they got, I thought, were actually quite impressive. They were also operating in reflection, if I recall correctly. So they could use the bottom gold both as a contact and also as a reflector, I think. They were able to show sort of uniform phase change and then eventually be able to make dynamic sort of beam steering structures. I think one of the challenges, phase change materials is not my area of expertise, but one challenge is just the optical absorption of the nano antennas. But I do think it's a complementary technique. One advantage it may have is that it can be a passive system. So if I change the phase of a nano antenna by changing its crystal structure, then I don't need to apply another voltage and it just stays there. Whereas for our system, we would need to continually apply a voltage. And so that might be one sort of difference. But I think I agree with you. I am very excited about these sort of resonant structures. And I think there is a lot of power here, and it can be this sort of universal sort of pixel that we can use to do whatever sort of wavefront shaping. But yeah, I think phase change materials is a really good, is also a very interesting platform. And I think a lot of the mechanical platforms that you had mentioned as well, putting them on polymers, stretching them around, is really exciting for a lot of demonstrations of the power of sort of this tuning. But yeah, you're also right that it's very difficult to, if you're going to stretch the entire structure, it impacts the response of every single antenna. Whereas here, we can eventually do things on single pixels and actually change around the response. So, yeah.
So, any more questions? Oh, actually, for the two-dimensional design, I cannot imagine how you would stagger this like the electrodes to control each unit, because there are so many of them. Like for 1D, it's straightforward to light them up in the space. But for if you want to control individual ones in 2D, do we make it a multi-layer system, like so that we can stagger in the Z direction like that?
So, that might be one way of doing it. I guess I would say that some of these problems have been sort of solved in the electronics industry, right? Like you have transistors, you have, a few billion of them sitting on a chip, and they all need to, the operation all need to talk to each other to perform the logic gates. And so you have these series of vias and metal connections that actually control all of them. So I think there's a couple of different ways of doing this. There's one paper from UCLA that, I think this was done while he was a postdoc in Harry Atwater's group at Caltech. But what you can do for basic things like beam steering and some lensing operations, you can actually use, if you have this sort of two-dimensional control, you can have a perimeter sort of architecture. So you have a series of circuits that connect each individual row or column together. And then you have, if I have n by n unit cells, I end up having 2n different elements that need to be controlled for. And so they were able to show, dynamic sort of beam steering in a couple of different directions and some basic sort of lensing operations. But if you want full control, for example, if you want to make a hologram, every single point in space, you need to be able to define the amplitude and the phase. And so to do that, you would need to have individual control where each nano antenna is controlled independently of all the others, in which case you would need a very complicated sort of system of vias and electrodes, things like this. And so developing that sort of system level understanding, I think, is, effectively, and designing that in your own clean room might be a little bit of a challenge. This is something that the circuit industry will think about quite a bit. Yeah.
I see. We have gone. Oh, Zhen has a question.
Yeah. I may have. Hi, David. Very nice talk. And I mean,
Thank you.
I may just have some like very general questions because I'm very far away from this research field. So
Of course.
I don't know a lot of fundamentals on this topic. I'm just curious, like basically what you are doing is to use some structured surface or some structures, nanostructures to control how light was going in certain structures, right?
Yep.
Yeah.
Yeah.
So in this way, I'm just curious, like, I mean, because I'm not so sure how those kind of light controlling is useful in making chips, because you are using this as a way of transmitting signals, or yeah. So my question is it like possible, like, because I can see that using the structures, you can control the behavior of light propagation, and is it possible to use as a way of computing? Is like
yeah, no, yeah, absolutely.
Yeah.
So there's a whole field in sort of silicon photonics. On a chip, you might be able to use light and designing sort of these Mach-Zehnder interferometers. Long story short, you can actually perform logic operations on signals that are coming in and out. And so you can actually do very fast computation because you're able to go basically, at the speed of light in that material. And so I think, there's a lot of opportunities in that space for sure. At the end of the day, I think the design needs to be done very well, and it needs to be very efficient to compete with electronic circuits. So if you want to do computation at the same sort of energy levels that a standard circuit is operating, that places a lot of constraints on the amount of optical power you can send through your structure. But there's a lot of startup companies that are starting to look at that sort of space, and there's a lot of academic research. And actually, I think the nearest term application is actually in data centers. So one thing I didn't, sort of show is that there's actually an insane amount of energy is actually used in data centers these days. It's like several percent, approaching 10% of the total global energy usage is actually used in data centers for your Facebook, your Google, your everything else, data storage, the cloud, all of these things. And so there's a massive amount of power that's being used there. And the biggest bottleneck and one of the biggest energy sources is actually connecting each of the different server racks together, because the electrical interconnects are actually very, 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 like you just generate a lot of heat, and therefore you lose a lot of energy to heat in doing this. And so being able to convert this information to the optical domain and sending it along in fiber and connecting individual servers on a rack is one way of actually reducing that energy load quite substantially. And so having these sort of optical transceivers is what they're called, I think is the way that sort of data centers are really sort of going. And so, the ability to have an electrical control of light allows us to transfer all this information in that way. And I think it's a stepping stone towards exactly what you were saying. Yeah.
Okay, thank you so much.
So we have another question from Professor Peijun Guo from Yale, and he will ask it in live.
Hi, Mark. Wonderful talk. Thank you. So I have a question about lithium niobate. So what's unique about the lithium niobate that makes it compatible for thin film growth? So do you expect that other higher nonlinear Chi2 nonlinear materials such as beta barium borate or other kind of nonlinear materials could also be grown or have a potential to be grown into thin films to enable more optical chip platforms?
Yeah, no, absolutely. So there are definitely materials that have higher Chi2s. I think, you mentioned BBO. Barium titanate is also another good example. Here, lithium niobate has been used in bulk optical systems for a while, and being able to, they basically will grow very large single crystals using a congruent growing method. So they can actually do it in a style of growth that's similar to silicon, Czochralski style growth, and get single crystals that can be actually put onto 6-inch wafers. And then they go through the same sort of preparation for thin films like you would have for SOI. And so I think in the future, yeah, being able to grow large enough single crystals of decent, of high quality and being able to do the wafer bonding, I think, yeah, that would definitely be worth exploring. I don't know offhand. I'm sure BBO has a relatively high refractive index, but yeah, there are a lot of sort of considerations for what materials to sort of to work with. I know. I think IBM has been very interested in trying to use barium titanate, thin film barium titanate, and so I think there's probably a lot of very interesting work to be done in academic spaces, growing some electro-optic materials or Kai2 materials in thin films for this sort of for these sort of technologies. If it's going to be scalable and deployable, you need to be able to grow very high quality, very big crystals. And so, yeah, if you can do that, I think that would be like, I would be surprised if that wouldn't appear on the market at some point in the future. I guess one thing, we are sending in both microwaves and optical, photons. And so there's a lot of considerations in looking at what the optical properties are at microwave frequencies and at optical frequencies to be able to inject or get as much of the light or get as much of the microwave field actually into the electro-optic material. And so for some of these materials, if you have an extraordinarily high microwave refractive index, that might be one limiting factor. But offhand, I don't actually know any of the numbers for materials like BBO. But yeah, that sounds like a great idea.
Thanks very much.
All right, so if we don't have more questions, shall we finish here?
Yeah. Do you have more questions, Jingtian?
Oh, I do. Okay, thank you, David, for the great talk.
Yeah, absolutely. Yeah, thank you for the invitation.
Yeah,
thanks for the.
Oh, sorry, Zhen, you can.
No, I'm just saying thanks for the talk. I mean, that's it.
Yeah, it has been a nice discussion. It's quite a little bit early for me.
Yeah, 7 a.m. is yeah.
All right, we can finish here. I will follow up with you on writing a recap. I will write it and let you take a look. And we can upload the recordings.
Okay, yeah. Let me know when you finish editing, and I'll let you know. Yeah.
You want to take a look at the recordings ahead, right?
Yeah, I'd like to see the recording ahead of time.
Yeah, sure. Okay,
cool. Yeah.
Yeah, great. Yeah, thank you so much. Yeah, I guess your day is just starting. And some people's days might be just ending, but yeah. Thank you for the,
so much for the opportunity. Nice talk.
Yeah, thank you. Yeah, some great questions, and yeah, best of luck, and yeah, great.